Moving on then to the second part of a finite element analysis, and that is the material properties. In SEEP-W and in all GeoStudio products, materials are first created and then they are assigned to the geometry. We will go through this process in a little bit. SEEP-W has two main material property requirements. One is the volumetric water content, and we have to describe it as a function. The other is the hydraulic conductivity, and when the soil is saturated we refer to it as Ksat, but generally when we have unsaturated soil the conductivity needs to be described as a function that is very similar to the water content function. To get the idea of why we need a function, we can look at this graphic. And when we expect an unsaturated zone, we need to have a conductivity function. Ksat only works for saturated zone. So when all the pores or voids are full of water, we are saturated. A molecule of water might follow some path like this through the soil. That is the easiest path and the least resistant path that it could take. Water is fundamentally quite lazy, and it is looking for the most simplest path and the one that takes the least amount of energy to go from point A to point B. Then if air begins to enter the sample, water has drained out of the soil, and some of the voids are filled with air. Now it is more difficult for a droplet of water to pass from point A to point B. Now the path may have to be something like this. More energy is required to flow through this tortuous path, and as a result it is more difficult. And we describe this increased difficulty with a lower conductivity value. There comes a point when there is so much air in the sample that the water is not continuous. There is no liquid water path through this sample. And as a result, liquid water cannot flow through this condition. And when we reach the point where there is no path of continuous liquid water, we say we have reached the residual water content. So we move all the way from the saturated condition to the residual condition. And all of this depends on the degree of saturation or on the amount of air voids that are within the sample. And to repeat, this is the easiest and this is the most difficult. And the degree of difficulty we describe with variation in the hydraulic conductivity. So here then is the shape of a volumetric water content function. First of all, on the horizontal axis we have plotted pore water pressure. Here the pore water pressure is 0. On the right side of 0 the pore water is positive, and on the left it is negative. And so when the pore water pressure is 0, we have a particular volumetric water content here, and this is equivalent to the porosity of the soil. It is the porosity of the soil, a value that is quite easily determined for a soil sample, so it already gives us a really good anchor point on this graph to reference the function. As water begins to drain out of the sample, the water content can decrease a little bit, but pretty soon air begins to enter the sample, and we call this the air entry value, or often the AEV value. It is the air entry value. Then water begins to drain out of the soil, and it continues to drain out of the soil as the pore pressure becomes more and more negative, or in other words, as the suction increases, the water content goes down, 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 and we reach what is known as the residual water content. We will see in a little bit later what we mean by residual water content with a physical illustration. So the key elements are the porosity, or the volumetric water content at zero pressure, the air entry value, the residual water content, and the rate at which the curve diminishes, or the slope of the curve. And the slope here, the slope is related to the grain size distribution. We will talk about this more at the end of session 1. So for very granular materials, the slope might be very steep. For clay soils, it might be very flat. So the slope is related to the soil particle distribution and the size of the distribution of the voids. Let's talk a little bit about terminology. The water content function, notice that it is volumetric. It is not gravimetric. And you will find in the literature that many people use the terminology soil water characteristic curve. Soil scientists tend to use water retention curve. Sometimes the curve is presented in terms of degree of saturation instead of volumetric water content. We will use volumetric water content function in SEEP-W. To us, it seems the most intuitive description of this function, and so we have elected to talk about the volumetric water content function in SEEP-W, but in the literature you will find all these other terms that mean exactly the same thing. So as we already have illustrated, if a soil experiences negative pore water pressure, then the conductivity is not constant. It's more difficult to flow when there are air pockets inside the soil. So conductivity is a function of water content. Indirectly, conductivity is also a function of the pore water pressure, particularly the negative pore water pressure. And therefore, the conductivity function, the K function, derives its fundamental shape from the volumetric water content function. And as we will see later, we often use the volumetric water content function to establish or estimate the hydraulic conductivity function. The shapes of the two curves are very similar. So here is the shape. The shape of the curve looks exactly the same, and when we are at zero pressure, or we are on the positive side of pore pressure, we say we have the saturated hydraulic conductivity. The saturated hydraulic conductivity does not change greatly until we have some air that begins to enter the sample, and then the conductivity begins to drop. Once again, as air enters the sample, then it is more difficult for water to flow through the soil. It takes more energy, and we describe this increased requirement for energy by a decrease in the hydraulic conductivity. To illustrate this a little further, we have some graphics here in the context of the volumetric water content function and the conductivity function. Once again, here we have a sample that is completely saturated. And you will see that there is a path through liquid water, and under these conditions we have K sat here, and we have the porosity. Then when air begins to enter the sample, the degree of saturation is less than the saturated case, and so a droplet of water would have to take a more circuitous route through the sample, and in this case the difficulty starts when air begins to enter the sample, and then ultimately when the soil drains to the point where there is no continuous water path, then we reach the residual water content. And on our volumetric water content function, it is somewhere here. The hydraulic conductivity becomes very low, and it gets so low that it really means that there is no flow through the soil. Often this curve is also drawn this way, although it doesn't really matter what happens here. The point is that the conductivity is so low that there is virtually no flow. We can illustrate these concepts a little bit further with a very simple experiment. If you take a paper towel and wrap it around something like a ruler, and you put the paper towel in a cup of water, and maybe the water has some food coloring in it, such that we can see the water in the paper towel. As you all know, that the paper towel is very absorbent and water will rise in the paper towel. What is interesting here that we can make some assumptions about the property of the paper towel, and we can simulate this phenomena with SEEP-W. So it is obvious that we have a zone here that is much darker, and you all know that this is often called the capillary zone. This water in the is saturated, or the paper towel here is saturated. But notice the change in color. So there's less water content here. And here we see slight shading. There's water there, but the water content is so low that it still doesn't show up any of the dye. The purpose of showing this is to illustrate what is the pore water pressure here. And as you all know, the pore water pressure is negative there. And the second purpose here is to illustrate how that the pore pressure distribution in the paper towel and the water content in the paper towel are a direct reflection of our definition of the volumetric water content function. So let's look at this situation a little bit more carefully. And let's plot on this side of the curve here the volumetric water content, and on this side the pore water pressure. Well, I think you can all agree and would readily tell me that the pore water pressure above the water table, so to speak, is negative, and in all likelihood you would tell me that the pore water pressure is negative up to the ground surface, at least over a large distance, hydrostatically negative. So the pore water pressure is negative. Now maybe this curve isn't exactly linear, but the main point is that the pore water pressure is negative, and it becomes more and more negative the higher we go in this direction. Now you all probably would also be able to say that at the level of the water that the water content is equal to the saturation water content. And then we have a capillary zone where the water content doesn't change very much, it remains saturated. But then as the pore pressure begins to increase, the water content in the paper towel diminishes, and finally we get into a very dry area of the paper towel. And we saw this with the paper towel that was sticking up in the cup of water. Now, if you turn your head, then this is a reflection of the shape of the volumetric water content function. So this is the capillary zone. So let us see if we can simulate this situation in SEEP-W. Let us assume that the paper has some properties. These are purely fictitious properties. They have no bearing to reality. No attempt has been made to actually define the actual properties for the paper towel. We have simply made up some properties to illustrate the point. So we are going to start by saying that the porosity is 0.8. We are going to say the air entry value is 2 kPa, or approximately 20 centimeters or 200 millimeters of water. And we are going to arbitrarily say that the water content, the residual water content, is 0.1 when the negative pore water pressure is 10 kPa. Then we are going to say that Ksat is 1 meter per second, and the hydraulic conductivity drops off to 1/100th of that, or 0.001 meters per second, by the time we get down to 10 kPa. So let us go to GeoStudio and open up SEEP-02 paper towel. File, open, SEEP-02, and I will click on my All Objects Zoom button, and we have analyzed or set up the problem here for you, and we are going to do a steady state seepage analysis. So to begin with, under Key In Analysis, notice that we have selected steady state. We have selected a steady state analysis. To begin with, let us look at the material properties that were defined. Under Key In, hydraulic functions, volumetric water content. We will spend more time on how to define these functions, but for the time being, click on paper water content function, and you see here that we have our volumetric water content function. We said that the porosity was 0.8. We said that the air entry value would be at 2 kPa. And we said we would drop down to 0.1 by the time we get to 10 kPa. So there is the paper volumetric water content function. Then we go Key In, hydraulic function. Again, click on paper K, and here is our hydraulic conductivity function. And once again, we said under saturated conditions, the conductivity was 1 meter per second. By the time we get to 2 kPa, we were going to start dropping the hydraulic conductivity, and we have dropped it 3 orders of magnitude by the time we get to 10 kPa. Now we have to do one other thing, and that is define a boundary condition. And I know we're jumping ahead of ourselves here, but for the time being, simply go draw a boundary condition, and from this drop-down list here, you will see the orange boundary condition called water in the glass, and we need to assign this boundary condition. In this particular case, what we're going to do is assign the boundary condition to a region. So all the paper that is below the water table, so to speak, we are going to apply this particular boundary condition. Very briefly, the boundary condition is a total head of 0.8 meters. Recall from our discussion of defining total head that at the water surface the elevation is 0.8, the pressure head is 0, therefore the total head is 0.8. The same for the bottom of the paper. The pressure head is 0.3, the elevation is 0.5, so once again the total head is 0.8. We can click on the Solve button and resolve this problem. And then we go to the Results view and go to Draw a Graph. First of all, the pore water pressure. Notice that we have plotted here the y-coordinate. The water level in the glass, we said it was at 0.8 meters. Notice that all of the pore water pressure here is negative. Negative pore water pressure. And in this particular case, it's negative, but it's hydrostatically negative all the way to the top of the paper. There is a reason as to why this is a straight line, but I won't take the time to go into that at this stage. The point here is that the pore water pressure is negative. We can then plot the volumetric water content function, the volumetric water content profile. And now notice that the water level is at 0.8 meters, and so we remain at the saturated water content until we are at elevation 1 meter. This distance is 200 millimeters, and recall that we said that air would begin to enter the paper when we were at a pressure head of about 200 millimeters or 2 kPa. And that is exactly what you see here. Now the water content is beginning to diminish, and finally we reach a point where the paper is very, very dry. So the SEEP computed water content profile is a direct reflection of the specified volumetric water content. Very briefly, the hydraulic conductivity looks much the same. When we were saturated, then we had a hydraulic conductivity of 1, and the hydraulic conductivity remains at 1 until we begin to have air, so to speak, in the paper, and then the hydraulic conductivity diminish very rapidly the drier that the paper gets. We can close this and go back to the results view. So the purpose out of this little experiment is to demonstrate that the concept of a volumetric water content function, hydraulic conductivity function, and the fact that we have such a thing as a capillary zone, and then once we get above the capillary zone, the water content diminishes, the hydraulic conductivity diminishes, and the exact thing that we see in a paper towel, we can simulate that with SEEP-W. Here are just different pictures of the computed volumetric water content functions. I won't spend any time on here, except that we often present these in terms of a log scale. If you plot them in terms of an arithmetic scale, you will notice that these functions are incredibly steep. Here are the hydraulic conductivity functions on a log scale and on an arithmetic scale. And on arithmetic scale, notice how extremely sharply the hydraulic conductivity drops off over very small changes in suction or negative water pressure. Now, once again, we had plotted the volumetric water content profile in the paper, and if you turn this 90 degrees counterclockwise, you see the volumetric water content function. So this profile in the paper is a direct reflection of the function. And we have already talked about the pore water pressure being negative, hydrostatically negative above the water level in the cup. So there are some important points here. SEEP-W simulates the concept of a capillary zone. The pore pressure in the capillary zone is negative, but where in the capillary zone it's negative but saturated, and as a result we often refer to this as a tension saturated zone. Lastly, the water content above the water table is a reflection of the specified volumetric water content function.